All right, so today we're going to talk about sources of magnetic fields. What produce magnetic fields? You know? And again, we've learned that these Maxwell's equations uh, explain all classical electromagnetic phenomena. Okay, so magnetic fields are denoted by B, and this equation. So these are differential equations, and here's an integral equation with the same information. The equations tell you the configuration of how the relationship between the configuration of the current and the magnetic field. Okay. Anyway, so on these equations, the right hand sides are the causes and the left hand side are the effects. Okay, so this equation is telling you that currents produce magnetic fields. It's also telling you something else. It's telling you, see, time varying electric fields also produce magnetic fields. Okay. Now, in this chapter, we'll just concentrate on this part of the equation. And then we'll devote an entire chapter to this part of the equation. Okay. So we will study this piecemeal. Okay. And now the form of the equation, this form tells you the following, that if you have an infinitely long straight conductor carrying a current, the magnetic field will be like this. You draw concentric circles around it, and the magnetic field will be tangent to that. Okay? And so the rule is the following. You use your right hand, stick your thumb out in the direction of the current, and the magnetic field lines will be wrapping around that field, the current. Okay? And of course, the further out you are, what do you think will happen to the magnitude of the magnetic field?
Go down.
It'll get weaker. Okay? How far is the magnetic field extending? Infinite. Okay? So what we'll be studying is magnetostatics, meaning we'll say that the current has been flowing forever. This, when you flip the switch, the magnetic field is getting established at the speed of light. Did you guys understand that? So let's say there was an infinite wire, there was no current, and then you flipped a switch and you started the current. The magnetic field just instantly didn't fill the entire universe. It started at the speed of light. It filled at the speed of light. But we are going to consider only the steady state case, okay? So the current has been flowing forever, and then we're studying what is the magnetic field, okay? So this is the subject of magnetostatics. I'm saying a lot, but anyway, all this chapter is about is this part of the equation. Okay, what does this say? Moving charges produce magnetic fields. Yeah. So I just added this thing, pulled out, copied an image from the internet. So here's a moving charge. A moving charge produces both electric and magnetic fields. By the way, this image is wrong. The magnetic field should be in this direction. But I couldn't find a correct image, so so there you go. All right. So the magnetic field should be like that. Okay. So a moving charge produces both electric and magnetic fields. And in this chapter, we'll just talk about the magnetic field. We'll ignore the electric field. Okay.
My friend Dan Joy is taking calc too. He wants to know if he can sit in on the class.
Yeah. Okay, so again, when we talk about stuff, we want to keep it as simple as possible. We won't talk about the electric field. We'll just talk about the magnetic field. Okay? Here's a comment about the electric fields. Okay. Here's a charge that is stationary, and it produces electric fields like that. When it starts moving, what happens is the electric field in this direction, the magnitude decreases, and in the perpendicular direction, it increases. Okay, so that's what happens to the electric field. Yeah. Now, all right. So now let's start talking about the magnetic field. Okay, again, this diagram, the magnetic field direction is like that. All right. All right, so moving charges as well as time varying electric fields produce magnetic fields. We're just going to talk about magnetic fields produced by moving charges. Okay, so here is the charge. And for now, so what is the simplest motion you can think of?
Linear.
Linear. So linear motion at constant velocity, and that's what we're going to do. Our charge is going to move at constant velocity, and so its magnitude and direction are constant. Okay? And we'll look at the field produced by that. Okay, and the rule is the following. You stick your thumb out in the direction of the motion, and it'll be a positive charge. And everything we say, if it's a negative charge, you just flip it. Okay? And your fingers point in the direction of the magnetic field. Okay, so the charge is moving along the axis of a cylinder, and the magnetic fields are tangential to the cylinder. The further out you are, the weaker the field will get. Okay? This charge is a charge, so we'll give you an expression for the field produced by this guy, but that is sort of an effective expression. That's true only if you have an infinite stream of charges and they've been moving forever. Okay. So anyway, all right. So now we'll give you the effective field produced by this guy. Okay. There's the direction. Okay. And here is the expression. Okay. So here is the charge moving at constant velocity. Okay. It's moving in this direction. The r hat vector, if you're trying to find the field at this point, r hat is a unit vector pointing at that point. Here's the velocity vector, and the angle between the velocity vector and the r hat vector is that. Okay. The magnetic field is given by mu naught. That's mu naught is a constant. It's called the vacuum permeability. That is the constant. Divided by 4 pi. Charge of the particle. Greater the charge, greater the magnetic field strength it'll produce at that point. V cross r hat. Faster it's moving, greater the magnetic field. Okay. And you see it's a cross product, and so the direction, so that'll give you the direction of the magnetic field. So if r hat is there, V is there, V cross r hat will be a vector coming out like that. Okay. So that's the direction of the magnetic field. And you can see that the further out you are, the field falls off as 1 over r squared. You can see that if r hat and V are parallel to each other, the cross product is 0. So this moving charge doesn't produce any magnetic field along its axis. Okay, so those are the only points where it doesn't produce any magnetic fields. Yeah. So that's the expression. All right, so let's say if you had, so that's the field due to this guy. What if you had 10 charges close by and they were moving at the same speed? What do you think the magnetic field would be at that point?
10 times it.
10 times it. That's the expression here. How do you get a bunch of charges moving? Okay, you pass a current in a wire. That's a bunch of charges moving. Each charge is producing a magnetic field there, and you just add them up. Okay, so that's what this is. This is the number of charges times q times their velocity, and that reduces to the current times ds is the length. Okay, and so that gives you the total number of charges moving times the speed. Okay, so that this part, what it would give you is n times q times v. Okay, so if you have a bunch of charges moving, so that's the magnetic field produced at that point due to this element of the current. what if you want to find the field due to the entire wire? What do? Integrate. Okay. That is the field at this point due to this guy. You want to find the field due to the entire guy. All you do is do this integral. Okay. Now, if this wire is in this plane, the magnetic field will come out. It will be perpendicular to this plane. But if this wire is going in and out of the plane, then you would have to add vectors in all the directions. What I'm trying to say is this integral is impossible to do unless it's a very simple case. Okay? So this is in principle how you would calculate the magnetic field due to a current carrying conductor at any point. And I already told you this integral is impossible to do, but for very simple cases. What do you have to do to find the field there? Do another impossible integral. All right. But what we have learned now is moving charges produce magnetic fields, and we have in principle an expression to calculate the magnetic field of this. Okay? So now I'll show you some simple cases where somebody's already done the integral for you. Okay? So here is the magnetic field due to this current carrying conductor. Now I gets pulled out of the integral because it's constant. Okay, and then ds cross r hat r squared. So here's the simple case. So for an infinitely long conductor carrying a straight conductor, if it has kinks, then you won't be able to do the integral. It has to be infinitely long and straight. And somebody's done the integral, and so see the magnetic field lines are concentric circles around that. Okay, the field at any given point is tangent to that. Okay, and the magnitude of this field is mu naught I over 2 pi a. A is the distance from the wire. Okay, so that integral was done for that case. Mm-hmm.
So A is the distance from the wire?
Yeah, the diagram shows you. Okay, so I don't know why the author chooses A, R with R as general. So if you have a circular current like that, it produces magnetic fields like this. I mean, we've drawn field lines. These are measured field lines, but we don't have an expression for this. We can't give you an expression for this. Okay. See, these are the magnetic field lines of a current carrying loop of wire. Look at this. These are the field lines produced by a bar magnet. See, they look very similar. That's why we call this an electromagnet. Okay. Okay, so a current carrying loop of wire is an electromagnet, and it's very versatile because you can change its strength, you can turn it on and off, you can flip directions, and so on. Okay. Speaking of flipping directions, so here's the field due to a current carrying conductor. Okay. So, oops. Here's the Earth's north and south pole. And we have a magnetic field, and the field is like this. Okay. As if a north pole is under the south pole, and the south pole of the magnet is under the north pole. Okay. So when you take a little compass, it points in that direction, it aligns there, and it points north. But now that you've seen this, now that you've learned this, well, fields are produced by moving charges. So the Earth's magnetic field is really produced by a current flowing in that direction. And the current is in the liquid outer core that flows. Now, we've discovered that in the last 60, 70 years that this current flips directions. So if you were on Earth 800,000 years ago, the current was flowing in that direction. And your compass would be pointing in that direction. Right. So the current flips on the average in 250,000 years. We don't know why it flips. And it flips within about 3,000 years, so roughly. So in a blink of an eye. Okay? And right now we're in the middle of a flip. Yeah. All right. So anyway, so see the field lines of a current carrying loop are very similar to that of a bar magnet. You know. Again, that integral, that impossible integral, this impossible integral has been done for a loop of wire along points along this axis. Okay, you can't do that integral for this point, that point. For points along the axis, that integral has been done, and there's the value of the integral. R is the radius of the loop, Z is the distance, vertical distance from the plane of the loop, current loop. Okay. All right. So this expression, I'll write down. There is R, and there is this distance is Z. Okay. And how do you find the direction of the magnetic field at this point? What is the direction of the magnetic field? Yep. And so this time you point your fingers in the direction of the current, and your thumb points in the direction of the magnetic field. So at this point, the magnetic field is pointing like that. At this point, it's pointing like this. Okay. And again, so there's that expression for points along the axis. Now, if R is much smaller than Z, if you're far away, then you can throw away this term, R. Okay. It's negligible compared to that. And that is what this expression is. Okay. So for far away point Z, that expression reduces to this, and so this is the radius of the loop, and instead of Z, they've written X. So as you see, if you're 3 radii away, then the expression is anyway, it's falling off as 1 over x cubed. Okay. Mu just tells you the strength of this magnet. You know, a current carrying loop is a magnet, and the strength of the magnet is, how strong the magnet is given by the magnetic moment. And the magnetic moment, as you saw, is N, the number of loops of wire, times the current, times the area of the loop. Okay. So it doesn't have to be a circular loop. It can be any shape. A is the area of the loop. And the direction of the area is, again, given by this right-hand rule. Okay. Point your fingers in the direction of the current, and the area vector points in the direction of your thumb. So what produce magnetic fields?
Moving charges.
Moving charges. How do you detect magnetic fields?
Test charge.
Try again.
When the charge is deflected?
Huh?
When a charge is deflected?
W-
Like if you're like following a charge and it gets deflected off the magnetic field, you know there's a magnetic field there.
So when will it get deflected? Will it get deflected if it's at rest?
Or just didn't-
There you go. Moving charges produce magnetic fields, and to detect magnetic fields, you need moving charges. Whatever produces it is what you need to detect it. Yeah, very beautiful symmetry. All right, so moving charges produce magnetic fields, and moving charges are affected by magnetic fields. Okay, so let's take two wires that have currents in them. A current is a bunch of moving charges. These guys will produce magnetic fields around it. How far do they produce? I mean, it's been flowing forever. It'll produce magnetic fields all around it. And this guy produces a magnetic field all around it, here, and there's moving charges here. So this magnetic field produced by this guy will affect these guys. So two wires carrying current close to each other, they will interact. Okay? So it turns out that if you have two wires carrying currents in the parallel direction, they attract each other. What do you think will happen if the currents are in the opposite direction?
They repel each other.
They will repel each other. Okay? So parallel currents attract each other. Okay, so let me ask you this. Okay, these guys will attract each other. How about these guys?
Does it still-
These guys will attract each other as well. These guys will repel each other. Okay? But I can't give you an expression for this. The force of attraction. I can give you an expression for this. Okay? So again, it's some integral that you're doing that you can do in very specific cases. Okay? So two conductors, infinitely long conductors carrying currents in the same direction. The force per unit length of the wire, the attractive force is mu naught I1 I2 divided by 2 pi a. And if the current is in the opposite direction, the force is repulsive, and the magnitude of the force is given by the same expression. Okay. And notice, if one of the currents is 0, then the force is 0. Why is the force 0?
They're not both magnetic. Only one is.
One is producing a magnetic field, but there are no moving charges in the other to sense the magnetic field. Okay? So, all right. I'm going to remind you of Gauss's law for electric fields. So you might remember, so Gauss's law was the flux through Gauss's law was this surface integral, and the flux through that surface was equal to the charge inside divided by epsilon naught. Okay? So we'll give you a similar expression for, so charges produced electric fields. What produce magnetic fields?
Moving charges.
In currents produce magnetic field. Okay, so moving charges. So we'll give you a similar expression. Okay, so we'll give you some kind of integral for the magnetic field, and that'll be related to the currents flowing inside. Okay. Now currents are not point things, so they're line things, line charges. So this, it'll turn out that we'll relate the line integral of the magnetic field around a closed loop to the currents flowing inside the loop. And that's Ampere's law. Okay. So the Ampere's law says the line integral of the magnetic field around a closed loop is equal to mu naught times the total current threading that loop. Okay. And if you're going to, so here's again you're always using right hand, your right hand. If you're taking the line integral in this sense, a current flowing in this direction is positive and a current flowing in that direction is negative. Okay. So if you take the line integral in this sense, this current is positive and that current will be negative. Okay. So the line integral, if you take in this sense, these currents are positive and this one is negative. If you take the line integral in this sense, this current is positive, these are negative. Okay. When is this useful? This guy is very useful rather than, okay, when will we give you a new expression? Okay, you already had this expression to calculate the magnetic field, which we saw several pages ago, r squared. And here's another way to calculate the magnetic field. In some situations, this is easier to use. In some other situations, this is easier to use. Okay. In general, this will be a lot easier to use to calculate the magnetic field in symmetric situations. Okay. So for instance, this expression that we got, this was gotten from Ampere's rule. Okay. It's much easier to calculate it using Ampere's rule. All right, so again, in general, all these integrals are very hard to do, okay, except in very special cases. So this integral is also hard to do. If, for instance, if that wire was not straight, then you couldn't do this integral because you couldn't make simplifying assumptions. Yeah. And this integral is also hard to do. Okay. So the Ampere's law says you take the line integral of the magnetic field around a closed loop, and that is equal to mu naught times the total current that's passing through the loop. Okay, so using Ampere's law, you can show the following. So let's say this is a thick wire, and current is flowing this wire, and the current is coming out of the plane. That's what this is showing you. Okay, so here's a thick wire, and there's current flowing through the wire, and the current is uniformly distributed. Okay, what this says is, so if the current is flowing like this, again, stick your thumb out in the direction of the current, and the magnetic field wraps around like that. At the center, the magnetic field is 0, and as you go out further and further from the center of the wire, the magnetic field strength is increasing. At the surface, the magnetic field strength is the highest, and then as you go out further, it falls off. Okay, so that's what this graph. This is showing you the magnitude of the magnetic field. At the center, it's 0, and the arrows indicate the direction. At the surface, it's maximum, and then it falls off. Okay, that's what this expression tells you. You go buy a donut, wrap a wire around it like this. This is called a toroid. If you pass a current through it, it'll produce a magnetic field like this. Closed circular magnetic field. Anybody remember why would we need this? What's a, huh? I'm sorry?
It's a model.
It's the tokamak, yeah, the fusion reaction. Okay, remember? All right, so you could produce field lines like that. Okay, now it turns out that the field is the strongest here and weakest there. But if if the ring was very large compared to this dimension, you can assume that the magnetic field is constant, uniform throughout. Okay, and the strength of the magnetic field is mu naught, that constant, times N is the number of turns a wire per meter times the current. And you can see that if you want to make that plasma very hot, you want this field to be strong. And you can wind more wire, you can pass a higher current. Okay. How do you pass a higher current?
Lower resistance.
You make a superconducting wire. Okay. So, and so by the advantage of having a superconducting wire, it doesn't heat up. Okay. This is a solenoid. You take a cylinder and wrap it in wires. Okay, so let's. Here, so this is a solenoid. Okay, you just take a wire and wrap it into a cylinder, and you get a solenoid. So here's a closely wound solenoid, and in a closely wound solenoid, the field is uniform, and you can make a strong field. Again, the expression is the same: mu naught times N times I. N is the number of turns of wire per meter. Okay. Again, you can show this using Ampere's law. Okay. So like I said, Ampere's law is useful in calculating magnetic fields in all right, so you guys remember we talked about at CERN, there's this Large Hadron Collider, and that's where all the detectors are located. Okay, and it's a proton beam that goes around and collides, and the circumference of of the of this detector is 27 kilometers, we saw, or 30 kilometers, roughly from here to Ormond Beach. That's how big the circle is. Okay, and so where's my the beams are going around almost at the speed of light, and they'll collide, and this is the detector. Okay, and so they collide, and all the energy is deposited into creating new particles, and these particles fly out in the detector. This detector, this thing is as large as this building. So well, almost as large as this building. And inside this building, they have a uniform magnetic field. So that's what this picture is. So, okay, so here's, you can get the scale. So that's the inside of the detector. Well, the inside of the housing that this is packed chock-a-block full with detectors. That's just, and inside this, you have to create a strong, uniform magnetic field. And this is how you create the magnetic field. So, where is the solenoid magnet? Why did I remove that? Okay, so inside a solenoid, you pass a wire like that, and you can create a magnetic field like that, uniform magnetic field like that. So inside this region you have magnetic field, and so see all those guys, each of those pixels, these particles passing through a detector, it's tiny detectors. So this is a cross section, particles have collided, and with the energy released, energy, you have created all kinds of particles. So this is gold and gold nuclei colliding there. This is a proton-proton beam colliding there. Okay? And when a charged particle travels in a magnetic field, its track bends, and from the radii of the track, you can figure out the mass of the particle created. Yeah. So, what creates a magnetic field? Moving charges. So in atoms, you have these electrons moving about. So this is a classical picture. Yeah. And so that should produce a magnetic field. Okay, you just saw that current carrying loop produces a magnetic field like that. You know, it behaves like a magnet, like this. Right, so if an electron is going around the nucleus, okay, an electron moving like this is a current in this direction, okay, it would produce a magnetic field. The magnet would point in that direction. Right, so the strength of the magnet is the current times the area, and it equals this. It's the charge of the electron divided by 2 times the mass of the electrons times the angular momentum of the electron, orbital angular momentum. And you'll see in quantum mechanics tells you that the value of this angular momentum can only be that. Okay. L is the angular momentum quantum number, and L can take, so here's the nucleus. This is n equal to 1 orbital. This is n equal to 2 orbitals. This is n equal to 3 orbitals. And each of these guys have sublevels where L can take different values, and L can take values from 0 to n minus 1. So in this level, you can only have L equal to 0. And L equal to 0 is called the s orbital. For n equal to 2, L can be 0 and L can be 1. L equal to 0 is called the s orbital. What is L equal to 1 called? P orbital. There you go. Okay. So for n equal to 3, what are the values L can take? S, P, D. Okay. All right, that's what they are. Okay. We're not going to worry about all of that. Here's what I want to share with you. Okay. In an atom, each electron goes around the nucleus. Okay, so in 10 to the minus 16 seconds. Okay, so this is one of the orbitals you can think of. This would produce a field of 20 Tesla at the center of the nucleus. A single electron would produce a field of 20 Tesla. What is the strongest field we made?
100.
Some 100 Tesla. Very good, my friend. I almost gave you $1.
This is going back, but what did you say the H with the line through it was on the last equation?
Oh, that was H bar. That's the units in which angular momentum shows up.
It's a unit?
Yeah, it's a unit of angular momentum. It's a fundamental unit of angular momentum. So the strongest magnetic field we've created is about 100 Tesla. Here's a single electron creating a magnetic field of 20 Tesla. at the center of the nucleus. Why isn't every metal attracting to every atom? If every atom were such a strong magnet.
Strength falls off quickly with distance. Low curve.
Here. That's a 1.5 Tesla magnetic field in there. This is a gurney that flew across the room. Somebody flipped on the switch to the magnet, and that gurney flew across. So that magnetic field is very strong. And that's only 1.5 Tesla. If that electron produced that magnetic field of 20 Tesla, every gurney should be flying at every atom. So what's going on? So in nature, for every electron moving in that direction, there's an electron moving in this direction. Okay. Electrons in the s orbital, again, this is loosely speaking, they have zero angular momentum. It's like they're going through the center and back and forth. So, so it turns out that whenever there's an electron in the p orbital, for every electron there, you have a electron moving in the opposite direction. And if there is an odd number of electrons in an atom, it's always in the s orbital, so it has zero angular momentum. Okay. So in most materials, because of oppositely moving electrons, magnetic effects produced by orbital motion is either zero or very small. But electrons have spin, they're spinning, and so they behave like a magnet. And the strength of the magnetic moment of a spinning electron is that EH bar divided by 2me. And this is called the Bohr magneton, and that's the strength of that magnet. Okay, so remember this number. Well, you don't have to remember, I'll show it here in a second. So here are these atoms or ions. The hydrogen atom behaves like a magnet whose strength is 9.27 times 10 to the minus 24 joules per Tesla. So the hydrogen atom, it's behaving like a magnet, and the magnetic moment is that of the spinning electron. Okay. So the hydrogen atom has the nucleus there, and this behaves like a magnet whose moment is equal to the moment of the spinning electron. For helium, the magnetic moment is zero. Why do you think it's zero? It has electrons. So for the helium, here's the nucleus. And it has two electrons, and the spins are in the opposite direction. Okay, so they cancel each other. All right. So you see that atoms because there's moving charges in atoms, they have magnetic moments to them. Okay. Now, we'll keep things sort of simple. If you're classifying materials from magnetic perspective, there are three kinds of materials. Ferromagnetic materials, stuff that you can make strong magnets out of. Paramagnetic materials, they have weak magnetism, but using other magnets you can make those atoms align. and diamagnets. Okay, ferromagnetic materials, paramagnetic materials, and diamagnetic materials. Okay, in ferromagnetic materials, those magnetic atoms can interact strongly and they can line themselves up, and you can make a strong magnet out of them. The interaction is weak here, and this is antiferromagnetism. Here the interaction is such that the neighbors are antiparallel, and this is ferrimagnetism. The antiparallel one is a little weaker, so you can make decently strong magnets. Okay. Okay, so here's a strong magnet. Okay, what this is showing you is this is the size of a grain of sand, and in this grain of sand, all those sort of atomic magnets are all lined up. Okay, so there's about 10 to the 20 atoms in each grain, and all those magnets are lined up. But you see, each grain, the magnetism of all the grains are random in this sample. So this bulk sample is not magnetic. And if you want to make this bulk sample magnetic, you have to line up all the domains. Okay? And the way you line up all the domains is the following. You can line up the domains. So here's the domains are randomly oriented. What you can do is wrap a wire around it, pass a current through it, and then you can line up the domains. So that's how you can strongly magnetize this thing. Okay? All right. We won't worry about this stuff. I'll tell you about one little toy, and then we'll be done with this chapter. I mean, done with the lecture. So here's a big boy toy. Okay, so you can see that this would fit roughly in this room, maybe a little larger room. It's an electromagnetic gun. And here's what it can do. Oh man, this is amazing. A projectile launched at, it can launch it at 10 kilometers a second. What is the escape velocity from Earth? 11 kilometers a second, 11.2. Yeah, so it can launch it at 11 kilometers. So in this span, it is giving an object an acceleration of 5 million Gs. So it can apply a force equal to 5 million times the weight of the object. So you launch your physics professor, what will come out is a pellet. You can't launch anything with structure. You have to launch a solid object or something like that. Okay. Acceleration with speeds of 10 kilometers per second have been achieved. Okay, so how does this thing work? So imagine this: in a span of this length, you're going from 0 to 11 kilometers a second. Yeah, absolutely amazing. So here's how it works. That's why this is called a rail gun as well, but you can buy toy models of this. Okay, so here's a metal rail, here's the projectile, here's the fuse. When you want to launch the projectile, all you do is flip a switch and pass a current through this rail gun. The current passes through the fuse, it instantly vaporizes the fuse, makes it into a plasma. Okay. So here's the current. Here, so we'll say this is positive charges flowing in that direction, velocity. And this current also produces a magnetic field into the paper, or you can have a magnetic field if you want. So V cross B will be a this field needs to come out of the paper. V cross, oh no. Oh, V cross, yeah, into the paper. V cross B is a force in that direction. So this magnetic field on every plasma particle is exerting force in this direction, which is pushing the projectile. And you can exert a force of 5 million times the weight of the object. Okay. So all you have to do is flip a switch, and in a millisecond, you have achieved that speed. Yep.
Do they have like demonstrations of this that civilians can watch?
This guy has top secret clearance. He could go watch it. Well, I mean, it does.
I mean, you wouldn't.
Sorry. He doesn't have a top secret clearance.
Good thing you're not a witness protection.